Hello students, welcome to Sources classes. Today our topic will be vector analysis. So let's start with our very first sum. So here is our first question. It says consider the equation 2x plus 2y equal to 1 and 2x minus y equal to 1 over z3. So what is the solution? We need to find solution x, y. So let us write it here. The equations we have are 2x plus 2y equal to 1 and 2x minus y equal to 1. So solving these two equations, what we obtain is y equal to 0 and x is equal to half. So our solution to this question will be 1 by 2 comma 0. So let's check which point matches with this. So here we can see that 1 by 2 comma 0 is option number 3 D. So our correct answer to question number 1 will be option number D. So let us move on to our second question. So our question number 2 is here. It says what is the dimension of the vector space formed by the solution of the system of the following equations. So we have been given three equations. Let us write those equations. Equation 1 is x1 plus x2 plus x3 equal to 0. Equation number 2 is x1 plus 2x2 equal to 0. Equation number 3 is x2 minus x3 equal to 0. So now we can write the above system of equations in this form. It will be x1 plus x2 plus x3 comma x1 plus 2x2 comma x2 minus x3 bracket close is equal to 0 comma 0 comma 0. So this implies that x1 1 comma 1 comma 0 plus x2 1 comma 2 comma 1 plus x3 that is 1 comma 0 comma minus 1 is equal to 0 comma 0 comma 0. So here we can see that x1 comma x2 comma x3 all belong to R, and the dimension of this vector space can be said to be 3. So here we have a dimension of the vector space formed by the solution is 3. So our answer to this question will be 3. So now let's proceed to our question number 3. So here is our question number 3. Okay, so in question number 3 we can see that we have been given vector space of 2 cross 2 matrices, and our first matrix is W1 X Y 0 X, and our second matrix W2 is X Y Z and 0. All we need to do is find W1 intersection W2, dimension of W1 intersection dimension of W2. So let us find W1 intersection W2. So W1 intersection W2 will be a vector of matrix. We will have here X, here Y, here 0 and 0. So and this will be X comma Y belongs to R. So this will be our intersection, because here we have X and X common, and here we have Y and Y common, but in this 2 we don't have anything common, so we have to put here zeros. And now our dimension of this, so this will be our W1 intersection W2. So dimension of W1 intersection W2 will be 1. So our answer is B in of question number 3, that is 1. So let's proceed to question number 4. So here is our question number 4. It says this set. Okay, so we have been given two sets and we need to say about the linear independent or dependence of both the sets. So let's check set 1, which is equal to alpha equal to 1 3 minus 2 0 4 minus 1, and beta is a matrix that is 2 6 -4, 0, 8, and -2. And our second set is f equal to u cube plus 3u plus 4, and g is u cube plus 4u plus 3. So let's start solving this question. Okay, so let us take our set 1. So for set 1 we have alpha equals to 1, 3, minus 2, 0, 4, minus 1, and beta we have 2, 6, minus 4, 0, 8, and minus 2. So we can also write it as alpha equal to 1, 3, minus 2, 0, 4, minus 1, and beta equal to, we can take 2 common and we are left with 1, 3, minus 2, 0, 4, minus 1. So we can see that here we have alpha equal to 2 beta, which imply alpha equal to 2 beta. Hence S1 is linearly independent. S1 is linearly dependent. Now we need to check for S2. So let's check for S2. Here we have set S2, which is equal to f equal to u cube plus 3u plus 4 comma g equal to u cube plus 4u plus 3. So now let's proceed. We can say that af plus bg will be equal to 0. So now let's put the values. A u cube plus 3u plus 4 plus b into u cube plus 4u plus 3 is equal to 0. Simplifying this, we get u cube, in bracket we have a plus b, plus u, in bracket we have 3a plus 4b, plus 4a plus 3b equal to 0. So from this we can say a plus b equal to 0. This is our first statement. Now 3a plus 4b equal to 0. This is our second statement. Now here we can say, so this was our second statement, and our third statement will be 4a plus 3b equal to 0. So this is our third statement. So from this we can see that a, b both have values 0. A is also equal to 0 and b is also equal to 0. Hence S2 is linearly independent. Linearly independent. So we had S1 linearly dependent and S2 linearly independent. So let's check which of the option matches with our answer. So here we can see that option C is matching with our answer, where S1 is linearly dependent but S2 is not. So our answer to question number 4 is C. So let's proceed to question number 5. So here is our question number 5. So in question 5 we can see that W1 and W2 are finite dimension subspace of a vector space V, where dimension of W1 is 2, dimension of W2 is also 2, and dimension of W1 plus W2 is equal to 3. So we need to find dimension of W1 intersection W2. So we know that dimension of W1 plus W2 is equal to dimension of W1 plus dimension of W2 minus dimension of W1 intersection W2. So from this we can say that dimension of W1 intersection W2 will be equal to dimension of W1, which is 2, plus dimension of W2, which is also 2, minus dimension of W1 plus W2, which is 3. So solving this we get 1. So our answer to this question will be A, that is 1. So now let's proceed to question number 6. So this is our question number 6. It says in the vector space R, the coordinate vector of 3, 5, minus 2 relative to the ordered basis 1, 0, 0, 0, 1, 0, 0, 0, 1 is. So let us take an coordinate of vectors. So let alpha, comma, beta, comma, gamma be coordinates of the required vector. So from this we know that 3, 5, minus 2 is equal to alpha. Here we have 1, 0, 0 plus beta. Here we have 0, 1, 0 plus gamma 0, 0, 1. So this implies 3, 5, minus 2 equal to alpha, beta, gamma, which states that alpha equal to 3, beta equal to 5, and gamma equal to minus 2. So our required coordinates are 3, 5, minus 2. So it matches with point B. So our answer to question number 6 is option number B. So let us now proceed to question number 7. So this is our question number 7. It says the dimension of the vector space spanned by 1, minus 2, 3, minus 1 and 1, 1, minus 2, 3. So let us solve this question. So here we have two vectors given. So let alpha and beta be the scalars. So let alpha and beta be the scalars such that alpha 1, minus 2, 3, minus 1 plus beta 1, 1, 1, minus 2, 3 will be equal to 0, 0, 0, 0. So solving this, we will get here it's alpha plus beta, comma, minus 2 alpha plus beta, comma, 3 alpha minus 2 beta, comma, minus alpha plus 3 beta is equal to 0, 0, 0, 0. So let us take any two equations. Let us take this and this. So taking first two, we have alpha plus beta equal to 0 and minus 2 alpha plus beta equal to 0. So solving both of them, here we have solving both equations, we get alpha equal to 0 and beta equal to 0. So from this we can say that the dimension of the vector space will be 2. So our answer to question number 7 is 2. Now let's move to question number 8. So here is our question number 8. It says if S equal to vectors 1, 1, 0, 2, 1, 3 belongs to R3, then which one of the following vectors of R3 is not the span S? So we need to find a vector out of these 4 vectors in the answer, out of these 4 vectors which is not a span S. So let us proceed with this question. Here we have two vectors. So let us take 1, 2, 3 as a possible answer. Here we have 1, 2, 3 as a possible answer. So let us consider 1, 2, 3 and proceed with this option. So this will be equal to alpha 1, 1, 0 plus beta 2, 1, 3. So let me tell you that we need to take all the 4 options and try which one of the one is not the span. So I have firstly taken 1, 2, 3. You can take any of the 4 options and try. So let us check for 1, 2, 3. So here we have alpha plus 2 beta, comma, alpha plus beta, comma, and third is 3 beta. So here we can say alpha plus 2 beta equal to 1, comma, alpha plus beta equal to 2, comma, 3 beta equal to 3. So from this we have beta equal to 1. Putting beta equal to 1 in this equation, we get alpha equal to 1. So we have here 2 more. So here we have alpha plus 2 beta equal to 1 and alpha equal to beta equal to 1. So you can see that these two equations does not satisfy each other. Hence 1, 2, 3 is not a span in S. So our answer to this question will be 1, 2, 3. That is option number C. Now let's move to question number 9. So here is our question number 9. It says let S equal to 1, 2, 3, 1, 0, minus 1. The value of k for which the vector 2, 1, k belongs to the linear span of S is. So let's solve this. Here we have S equal to 1, 2, 3, 1, 0, minus 1, and we have a vector 2, 1, k which belongs to the linear span of S. So here we can say that 2, 1, k is equal to 1, 2, 3 plus, okay, that will be a comma, plus 1, 0, minus 1. So solving this we get 2, 1, k equal to 2, 2, 2. So our value to k will be 2. So our answer to this question will be option number C. Now let's move on to our last question, that is question number 10, which says the dimension of the subspace x1, x2, x3, x4, x5 and 3x1 minus x2 plus x3 equal to 0 of R5 is. So we know that dimension of subspace, let me write this, dimension of subspace is always equals to number of independent variable, that is independent variable minus number of constraints, so here we have independent variable are 5. So here we have 5 independent variables, 5, and here we have number of constraints is 1. So we have one number of constraints. So our answer to this question will be 4. So our correct option is option number D. So we have completed all the 10 questions.